So the advanced topics in numerical PDEs, so we already talked a bit about iterative methods for large-scale problems, and today we'll finish our discussion. So last lecture I taught, we tried to make multigrid working, and it didn't work at the end, right? So I found a very simple thing that I missed in multigrid, and it's actually a very good lesson to learn from my mistake. So we'll talk about that first. So once we go over iterative method, today we're actually going to start about error estimation and high resolution and high order methods. So basically talking about how numerical errors would manifest in the solutions of partial differential equations. And we are also going to be talking about how to improve the quality of the solution using high order and high resolution methods. Then we're going to be talking about optimization and adjoint, which is also termed backpropagation by the machine learning guys. So basically figuring out if you have a numerical solution, how do you use gradient-based methods to optimize the parameters to obtain your goal in design. We also, the fourth and fifth topic are tentative. We probably have time to talk about them, but I'm not sure if we have time to talk about all of them. So unstructured mesh, which really fits complicated spatial domains. And also parallel solution of numerical PDEs, which is really a very hot topic today. And finally, we are going to have a guest lecture. We're still scheduling this of interactive PDE modeling and simulation using COMSOL. So COMSOL is a software that, as I'm aware of, many groups at MIT uses. And basically what it does is it solves PDE using finite elements. So the input of COMSOL, unless there is some package already prescribed the PDE for you, is really the weak form. So basically, if you want to solve a differential equation that is not already built into COMSOL in one of the packages, right? What you have to describe is the weak form, as long as the boundary conditions, which, as you know, is part of the weak form. So basically, we will have a guest lecture of somebody from COMSOL actually coming over to talk about how to write the weak form in COMSOL and have it solve basically any PDE you want. All right, so this is really the topics in the remaining part of this subject. All right, any questions on this? Okay. So now let's actually come back to multigrid, and before we go into figure out what's wrong in the code I wrote in the last lecture, let's actually have a review of multigrid because it's been a few weeks. So the idea of multigrid is that an iterative method could converge very slowly, especially on large grids, right? So imagine you have just a single grid point, which means you're solving a single equation, right? The matrix is 1 by 1. No matter if you use Jacobi or multigrid method, it'll converge in one iteration. The reason is, so let's focus on Jacobi method, which is what we put into multigrid the last time. The Jacobi method for solving AX equal to B. So just to let us be consistent with what we wrote in the code, let's write AU equal to B. All right. And Jacobi iteration is an iterative method for solving a large linear system. It's splitting the matrix A into two parts, a diagonal plus off diagonal, right? So basically, if I can write A equal to a diagonal matrix, which is the diagonal part, plus off diagonal part, which is basically the remaining of the matrix with the diagonals being 0. Then the system is going to be transferred to D times U plus OD times U equal to B. And the Jacobi iteration is simply saying that I'm going to treat this part of U as unknown as the value at the next iteration, and I'm going to be multiplying the previous guess on the off-diagonal part. So that's basically the iteration of Jacobi. So if you write it in an alternative way, basically UK plus 1 would be equal to D inverse, because D is a diagonal matrix. It's very easy to inverse, very easy to invert. The inverse is just taking the reciprocal on all the diagonal elements. So D inverse times B minus OD times UK. We can start with any initial guess of U0. U0, a popular choice is being all zeros. And then through this formula, we get our U1. And we plug U1 again back into this formula, we get U2, etc., etc. Under certain conditions, basically under the condition that if D inverse times OD, right, if this has eigenvalues between what? -1 and 1, right? Let's see, put strictly between -1 and 1. Then UK would converge to the solution as k goes to infinity, right? So we can prove this through the error equation, right? So basically the proof is subtracting this equation from this equation, right? We get an equation for the error, the difference between U and UK. And so basically we subtraction, what we get is E equal to UK minus U, and we can show that if this matrix has eigenvalues between -1 and 1, the error EK is going to approach 0. All right. Okay. So that's our Jacobi iteration. And the problem with the Jacobi iteration is that the convergence could be really slow. If we plot the eigenvalues, so let's see, eigenvalues of D inverse times OD, the eigenvalues of Jacobi basically goes from +1 to -1, almost basically in a sinusoidal way. And if you look at the Poisson's equation, you can actually prove that the eigenvalues exactly lie on a cosine curve. So, and as you know, like the larger the matrix is, the more eigenvalues there are. So the first and the last eigenvalue would approach 1 and -1 with a speed that is to the square of the number of grid points. Right. So basically, so the lambda 1, for example, would be on the order of 1 minus the order of 1 over nx square. So basically what you get is an eigenvalue approaching 1 and another eigenvalue approaching -1 in a very fast rate. Okay. And therefore, because the eigenvalue is very close to 1, the high power of this eigenvalue, you need a very high power of the eigenvalue in order for the corresponding eigenvector to decay at a reasonable rate, right? As we know, like lambda 1 to the kth power, I mean, if you expand it asymptotically, is on the order of e to the minus whatever this value is, or 1 over nx squared times k, right? So this is true when nx is very large, when the lambda 1 is very close to 1. So basically what that means is my k has to be, the number of iterations I have to take has to be on the order of nx squared in order for me to converge to order 1 rate. So we need a very large number of iterations to converge. If nx, for example, is 4,000, as in the image I started to use in lecture last time, then the number of iterations is supposed to be 4,000 squared, which is like 16 million. We have to take that many iterations to converge.